In this example, we've been asked to solve the differential equation d2y dx squared minus 3dy dx minus 4y equals e to the negative x. I recall that this is a second order differential equation because the highest derivative is a second derivative. And I see that all the y, dy and second derivative terms have got constant coefficients. I also note that the right-hand side, where all the x's are, is not 0, and so this is non-homogeneous second-order differential equation with constant coefficients. I recall the standard procedure used to solve an equation of this type, and the first step is to consider the homogeneous case only. Writing out the homogeneous case using the dash notation tells me that y double dash minus 3y dash minus 4y is equal to 0. The homogeneous case is where the right hand side is equal to 0. The next step in the method is to write out the auxiliary equation. The auxiliary equation comes from assuming the function y is a solution of the form e to the rx. So y dash will have an r in front, y double dash will have an r squared in front, and I can write out the auxiliary equation without the exponentials by replacing the double dash with r squared, the dash term with r, and the y term with just 1, and that will equal 0. This is the quadratic which defines the left-hand side, and it's the auxiliary equation. I now solve this auxiliary equation to work out one of the three cases that I have. So factorizing the left-hand side gives me an r and an r. I think of two numbers that multiply to give negative 4, add to give negative 3. It's going to be a 4 and 1, and I need a negative 4 and plus 1. Quickly check that. Negative 4 times 1 is negative 4, and plus 1r minus 4r gives me minus 3r. So the solutions to the r values are r is equal to plus 4 and r is equal to minus 1. So I've got two different values for r, which is case 1 of the homogeneous three possible cases. So from that I write down the general solution for the homogeneous case, which we call the complementary function. Which we denote by YC. It's the solution to the homogeneous case of the differential equation. Remember, in that case 1, two distinct values to the auxiliary equation. So the general solution, a e to the 4x plus b e to the minus x. The general solution has two arbitrary constants, and my two values for r are the exponents, the coefficients in front of the x in the exponents of the exponentials. So I now turn to the right hand side. I want to try and find a particular solution which takes into account the right hand side. I note at this stage that the right hand side is a function of the form e to the negative x, and I see that part of my complementary function is that same form e to the negative x. So I have to take that into account when I come to choose my trial function for the particular solution. If I try and find a solution which is already part of the complementary function, the process breaks down. So just remember at this stage, looking at the right hand side, compare it to the complementary function. I see that I have the same type of function. So when I come to do the particular solution, which takes into account the right hand side, I trial a function yp which is equal to x times e to the negative x. Because I have e to the negative x, which is part of the complementary function, I can't just solve for an equation a e to the negative x as the trial function, so I go for multiplying it by x, and have ax e to the negative x. At this stage in the method, the next process is to find the first and second derivative of yp, substitute it into the original dE to try and solve for the coefficient here, little a. So the first derivative, yp dash, I remember that I now have a product of two functions, a linear term and an exponential term. So I'm going to do the product rule down here. The derivative of the first function is just a, and I multiply that by the exponential function, the second function. I'm going to add that to the derivative of the first function multiplied by ax. The derivative of e to the negative x is negative e to the negative x. So the minus 1 is being multiplied by the first function, which is ax. So the product rule actually gives me minus here, ax e to the negative x. There's the first derivative. I need the second derivative, yp double dash. The first term is not a product of two functions of x, it's just a single function of x. The derivative of that is minus a e to the negative x. And the second function, minus ax e to the negative x, is the negative of the trial function, yp. So I can put in the same product rule, but it's just a minus times my answer for yp. I could think of just doing the product rule again, so minus outside of the derivative of ax e to the negative x, again, is a times e to the x minus ax e to the negative x. Multiplying through by the negative 1 to get rid of the brackets here, adding what I can together, yp double dash can be written as minus 2a e to the negative x. Negative times a negative is a positive, so it's plus ax e to the negative x. I have expressions for yp dash and yp double dash. Next process in the method is to sub into the dE. What I'm substituting in is yp double dash, yp dash, and yp, and remembering the right hand side e to the negative x. So at this stage here, substituting in second derivative, which is minus 2a e to the negative x plus ax e to the negative x. The next term in the dE is minus 3 times the first derivative. So down here I'm taking minus 3 times this first derivative, yp dash, which is minus 3a e to the negative x. Minus 3 times this second term will make that positive, so it's plus 3ax e to the negative x. The last term on the left hand side is minus 4 times y, substituting in yp for y, minus 4 times that gives us minus 4ax e to the negative x, and that is equal to the right hand side, which is e to the negative x. I'm going to equate coefficients here of e to the negative x. I've only got to solve for one unknown, which is the a here. As I go through, there should be some things that cancel out here. I've got two types of functions here, x e to the negative x and just e to the negative x constants. And I can see that if I look at just the ax e to the negative x's, I've got one of them here and 3 of them here, which is 4, and minus 4 of them here. So if I've done this correctly, this will always happen. One of the types of functions will cancel out. On the left hand side now, I've got negative 2a e to the next minus 3 of those same types of functions, which gives me minus 5a e to the negative x, and that is equal to negative e to the negative x on the right hand side. Equating coefficients. The coefficients we're talking about are the coefficients of e to the negative x. In this case, there's just one sum to do, minus 5a must equal 1, which gives me a equaling minus 1/5. So that tells me exactly what the trial function yp is. I put a negative 1/5 x e to the negative x. The next stage in the method, though, is to write down the general solution. The general solution y now is the addition of the complementary function yc and the particular solution yp. So the general solution y is the complementary function. There it is, a e to the 4x plus b e to the minus x. I'll write that in here. Plus b e to the negative x plus the particular solution with the value of a that I've found, minus 1/5 into the trial function, which was the correct trial, minus 1/5 x e to the negative x. And that gives me the complete general solution to the second order differential equation. I know it was a second order d, so I have two arbitrary constants. If I was given some conditions at this stage for the second order d, I would need two conditions, whether they are initial conditions or boundary conditions, and I would substitute both of them in to solve for the two constants, capital A and capital B. I checked the question. I was not given any boundary conditions at this stage, and so the best I can do is to just leave the solution as the general solution here, the general solution to the second order differential equation with constant coefficients and non-homogeneous right hand side.